yeah, it's definitely working right now.
I looked at the national smoke map. We're actually in pretty good shape on that. We weren't for a while there. We had some real serious smoke going
We're
on.
getting some stuff that comes down through Colorado and is edging our way, but
Yeah.
I think this, latest weather patterns help.
Well,
Definitely,
and they kind of passed the time of year when they set the grass on fire around here, so that's kind of helpful too. Yeah, it was. I kind of look at the daily smoke maps and it kind of looks good, at least in that respect. Anybody else have anything they want to add? Announcements, go to the order.
Is everybody getting the groups IO emails? And you should at least get one every day. Janelle, who's not here, usually sends out that Earth Sky information. And then Russ has the groups IO sending you alerts about meetings. Everybody getting them, especially the new people. Okay.
do you know if Janelle's coming Saturday night?
No, that's part of that email I send out. I've only heard from the people that I said thank you. Doug's coming out.
I'll be there.
If
Yeah.
she doesn't, I'll bring the laser.
Okay.
She's unfortunately, Janelle will not be here tonight. She texted me earlier. I can text her and ask her later if you would like, and just kind of.
I'll throw my laser in the car either way, so
Okay.
I'll be there.
I actually got one for Christmas, so I could bring mine too. I think it's in Manhattan, and I'm mostly in Shawnee right now, so it's been kind of hard to keep track of what's where, basically. So having this sort of two residence life is,
Double life.
oh God,
Yeah.
it's surprisingly stressful. Anyway, anything else? Oh, I forgot to say hello to those who may be remoting in or coming in from outside. So welcome to the remote attenders as well. Okay, so again, here's a few of the other things that are coming up. June the 22nd, be a general meeting. I think that might be the solstice. Not 100% on that. I have to go check.
Close.
That could be the solstice. So we could be having our meeting on the day of the solstice. So maybe we'll do something related to the solstice as a presentation. What about member nights? Do we have anything we want to say about that?
We had a few people out at the last members night, which is nice because often we don't have members come out. Let's see. Justin was there, and was anybody here out there? And two others were there that had brought scopes.
Okay.
And I'm really bad with names, so I'm not going to risk it.
Well,
Yeah.
Sean was one that was.
Yeah.
Sean was out there, yeah.
And I think he said he'd be at the public night too, right?
Yeah, he's coming. He's going to bring his scope out,
Yeah.
which is great.
Was he happy with it?
He, as far as I can tell, he was happy with it, and he's bringing it out again for
Cool.
public night. So he's got that 9.25 Celestron. So he can probably get some good viewing. So it'd be nice to have his scope out there.
Yeah. Yeah, some night during a member's night, I need to get out there and work with my scope, which has been sitting out there collecting dust for quite a while now. But unfortunately, the last one was kind of I can't remember what was going on, but it was something. Anyway. Okay, so moving on then. Just to kind of, I sort of debate whether or not to do these news items, especially since Jan does such a great job of updating it. But there's a few things that popped up that I wanted to kind of point out. This is one that came in one of my feeds, and this is actually an opportunity for those of you that may have just some interest in data mining, I guess you could say. Maybe not so interested in the scope aspects, but interested in the kind of follow-up and investigation. This is a program that is being administered through the University of Arizona. I believe it's funded by NASA, where they're actually, crowdsourcing the job basically of detecting these things on imagery. And it's one of those things where I think people kind of assume that like AI tools take care of all this now, but it turns out that it's surprisingly difficult to detect these things with a machine. The humans are just really very much better at this. So this is an opportunity that if you're interested to kind of make a contribution without leaving your, wherever it is you happen to keep your computer. So I thought I'd kind of throw this one in there. It also has to do with asteroids, and of course that's at least indirectly what we're going to talk about tonight. So thought I'd throw that one in there just as an opportunity for some of you. I actually signed up for this and did a little bit on it, and it's I guess depending on your sense of fun, it's kind of fun. So anyway, this is another one that I thought was kind of interesting. We one of the things our club does obviously is NEO follow-up, and the practical importance of that is, I hope, fairly obvious, that in order to understand the nature of impacts and impactors, you got to know what may potentially hit you. This was a kind of interesting study. This was actually in the journal Science, I believe. I haven't actually read the paper, but I've kind of read some of the summaries of it. And so what they've determined on this is that really big stuff we're in no danger from right now, or at least little known danger, put it that way. So it's estimated that probably something that might actually that could cause an extinction level event, we're talking about a cataclysmic event here, is pretty unlikely for the next 1,000 years. So we're pretty safe from that. The meta message behind all this though, is that while there's no real danger of getting hit by, we'd be talking about something that would be, miles, an object that would be miles wide, basically. It would be comparable to the sorts of things that the impactors, for example, that caused the dinosaurs' extinction, or at least were contributed to that. This would be something on that scale. However, there's still a bunch of other things out there, and again, I think Gary could probably give you a fairly detailed, off-the-cuff talk about this. There's still a lot of relatively small things out there that could cause a pretty significant amount of localized damage. So this doesn't mean, the little tagline here, it's not completely all clear. And that's actually one of the things that I want to talk a little bit about tonight. It's kind of related to this story because we're going to talk about impacts and impactors and some of the history of that, at least the known history of that in Earth history. So I thought I'd just kind of throw this in there as well. And if you want to read these or you want to link to these, I did not build links into this presentation, but I can send you the links on these if you're interested in taking a look at those. But I thought these were two stories that were kind of relevant to tonight's topic. And here's another one. Of course, it's become kind of a tradition, right? I guess if you call 4 months a tradition of, what did they compare? What did the Jerusalem Times compare asteroids to this month? This one's a little dated because it was in honor of Star Wars Day, right? May the 4th. But they compared it to an asteroid the size of 6 Darth Vaders. All right. So I looked up Darth Vader, who is roughly 2 meters tall, which would make a Darth Vader asteroid about 12 meters, which is 39 feet, about 40 feet. So not a particularly large one, but again, kind of harking back to that previous little article there, a 40-foot diameter object passing through the atmosphere, depending on what it was made out of, right? There's lots and lots of different kinds of asteroids made out of different stuff. Depending on what it was made of, it would likely break up in the atmosphere, it wouldn't actually impact. However, it would probably cause a shock wave and other types of things that could be locally devastating. There's a interesting little website that you can actually simulate asteroid collisions with the Earth. You pick up a location. Actually, I'll show you a map I made of that here. And pick the size of the object and what it's made out of and how fast it's going and all these things. And it'll give you some idea, right? It'll make a hole this big. It'll burn this large of an area. It'll produce a shock wave over this. It'll kill this many people. It's, kind of a grimly fun thing to do, I guess. Decide what would happen if you dropped an object right on Central Park in New York or something, and what would happen in a case like that. But anyway, this is the asteroid size comparison of the month. So Darth Vader's is the one for me.
Appreciate they say it's part of a trilogy of asteroids.
Yeah. Actually, it's part of 6 of them now, or something like that. So anyway, if you're ever wondering about the size of this particular object, 2023. Is this one we looked at here? Maybe not. Anyway,
I mean, when we see them, they're not numbered yet, so.
That's right.
Well, I'm looking it up to see
Are you?
if that was one we turned in on.
Uh-huh, yeah.
Haven't found
Part
it
of a
yet.
trilogy of asteroids, yes, to pass the Earth on Star Wars Day. Okay, and finally, I guess maybe not finally, but you know, clouds are one of our biggest problems. And this came from a completely different source. This was I mean, my job obviously involves thinking about clouds a lot when I do climate modeling, and clouds are one of the big unknowns in climate modeling. So I pay attention to clouds. So I'm on this website that talks about different clouds and cloud properties and things like that. And they posted this one, and my first thought was, no, that can't possibly be right? Somebody photoshopped this. Well, if they're photoshopping it, it's a really darkly kept secret because nobody will confess to this. Everybody is swearing up and down that there's a cloud in the sky. I don't exactly know where this was.
Looks like Godzilla.
Looks like Godzilla, right? You know, you can kind of picture the Godzilla, you know, with these. By the way, somebody was talking. They were interviewing the guy who played Godzilla in those old movies. He wore that rubber suit, and he was talking about how they made that noise. You know, that Godzilla makes, that screeching sound. And these are the old movies, not the new ones. And apparently, that noise is a rusty swinging gate. They recorded this gate going, you know, and then they kind of changed the speed of it just a little bit, and that's what Godzilla is. So I saw one of those old Godzilla movies not too long ago, and it kind of ruined it for me. Because instead of thinking about this, you know, fearsome nuclear mutant monster, all I could think about was rusty garden gate. So anyway, I hope that doesn't, by the way, I hope that doesn't ruin it for any of you if you're Godzilla fans. Anyway, this picture really doesn't have much to do with astronomy directly, but I just thought it was kind of cool, so I thought I'd sort of.
So anyway, that one asteroid you had, that was the one Gary turned data on.
Okay.
The Tombaugh was probably down.
Okay. So this was one of the ones that we reported, or
Yeah.
Gary reported, the collective, we reported data on this. Okay, so moving on. I thought about the good constellations for this month and things that would be prominent in the sky. And I thought we hadn't really done a zodiacal constellation in a while, so I thought we would take a closer look on Leo, right? So Leo the lion. So here's constellation Leo. One of the things that I always kind of look for is this asterism right here that's called the sickle, and the first star, the lowermost star. I always think about it as also as the backward question mark, right? Because it kind of looks like a backward question mark to me. The kind of point of it is Regulus, which is the brightest star in the constellation. We'll talk about that here in just a little bit. The way that I always think about finding Leo, and again, this is where Jan is a great help because she's the expert on finding things in the sky, is, you know, the Big Dipper, right, has the pointer stars, and if you point them in one direction, they go toward Polaris, the North Star. If you point them in the other direction, they kind of point toward Leo. So if you kind of follow it along until you kind of see this sickle-y looking thing here, which the actual line of point comes kind of right in here somewhere, so it almost points at Regulus, basically. Then you'll be able to find Leo. It's a pretty good sized constellation, actually. It's got a couple of interesting properties. First of all, it's one of the constellations of the zodiac, which are kind of abused in astrology, but are important in astronomy, I think, because they lie along the plane of the ecliptic, which is the kind of plane in which everything orbits the sun, right? Or everything moves around the sun. So from the perspective of an observer of Earth, the plane of the ecliptic is where the planets move along. So when you watch the planets, if you watch them on a night-by-night basis, they move along the plane of the ecliptic. I think that's actually why they became the zodiac, the signs, right? Because the early astrologers, I guess, were actually pretty good at recording the locations of things. The idea that, you know, your behavior is determined by all that, I think, is a little shaky. But the understanding that they got of celestial movement is actually pretty impressive. It's kind of funny that my sign is supposed to be very kind of spiritual and believing in all this stuff, which is, I tell you, it's not me necessarily. So I'm not very true to my my zodiacal sign. But anyway, there's that goldish line there that represents the plane of the ecliptic, and you can see it passes right by Regulus. The other thing that is kind of noteworthy about Leo is that it's very close to the celestial equator. That's the kind of purple line right there. That's the celestial equator. That means that it's visible from both hemispheres, and it's visible typically through most of the year. So you can see it, but it's most prominent in the spring. In fact, we're kind of towards the end of the period of time when it's most easy to see. It's also a pretty big constellation. So one of the things I kind of like to do is talk about the stories behind all these things. So last month we talked about Lyra, right, the harp. And, the interesting thing, at least to me, about Lyra wasn't necessarily the harp itself, it was who the harp belonged to. Well, in the case of Leo, what is interesting to me, I guess, the mythological part that's interesting, isn't so much Leo itself, the lion itself, but the myth that it's associated with. And the lion is associated with the myth of Heracles. So Heracles, or Hercules, was, again, I looked up what is a charcoal pencil drawing, like a colored pencil drawing, of Heracles completing one of his tasks, one of his 12 labors that we'll talk about here in just a second. But there's Heracles. Heracles was the son of Zeus and Alcmene, and that's actually part of the story here. This is a picture of Heracles, or Hercules. He's typically depicted, or almost always depicted, as a very large, strong, athletic character. I picked this particular statue very carefully because almost every statue or depiction I could find on this was a nude. And, I like to think that we have a family astronomy club here, right? So didn't want to press the envelope here a little bit. So this was the only representation I could find that was not, a nude. Anyway, but it kind of shows that this was and Hercules is, of course, associated with the kind of strength and vigor and a mighty warrior, and, it kind of reflects in our language a little bit. We talk about, Herculean strength and Herculean tasks and all these sorts of things. Hercules is a half-brother of Perseus, of one of the other constellations, and Dionysus, who, as far as I know, doesn't have a constellation. And the fact that he's the son of Zeus and not the son of Zeus's wife Hera is actually part of the story. The story of Hercules kind of involves this couple, and I've mentioned a few times, when you start reading mythology a little bit, you find that the gods and goddesses and the various characters of mythology were just a really, really rotten bunch of, I don't know if you call them people or not, but misbehavior was kind of rampant. So Zeus was no exception to that. So of course, Zeus was the king of the gods and probably could do pretty much whatever he wanted, but he was also kind of a notorious philanderer, right? He was kind of noted for not necessarily honoring the marital vows all that well. And Hera was the goddess of love and marriage, so that was probably even more galling to her, that her husband was getting around as much as he did. And apparently part of his getting around resulted in the birth of Hercules. And Hera was not at all happy about that. She did not like Hercules. In fact, Hercules, or Heracles, was named Heracles, which means something like in tribute to Hera, intentionally by Zeus to try to placate her. And apparently it didn't work. In fact, it didn't work so much that at one point she sent a snake to try to bite and kill the infant Heracles. And didn't work. Heracles was, I guess, mighty at that, even as a toddler or an infant. Killed the snake, right? There's several statues you can see of paintings of the baby Heracles killing this snake. Survived that attempt. It wasn't the only one. Hera had a hard time kind of letting this go. And at one point, she decided to kind of use the nuclear option, I guess we could say. And she actually made Heracles insane. She used her goddess powers to cloud the mind of Heracles in a way that made him murder his family. Of course, he was, at the time, I guess, he would plead temporary insanity. Now, I don't know if there's anything in our current legal code that's temporary insanity due to curse by a goddess. I don't know if that's ever appeared in any of our legal proceedings, but you never know. It's lots of other weird things that happen out there. But at any rate, so Heracles murdered his family. And Zeus, of course, partially because of his familial attachment, but also because he kind of understood the kind of injustice of that, decided essentially to go easy on Heracles. So instead of just banishing him, he gave him these 12 labors that he had to perform. And those 12 labors are kind of part of the myth now, right? We think about Herculean tasks, right? That has its origin in the 12 labors of Hercules. And these generally involved fighting some mythical creature or performing some feat of strength or something like that. So this is a tapestry that shows the 12 labors. Well, here's where Leo comes into play. The very first Herculean task was the slaying the Nemean lion. And that's what Leo represents. Leo in the sky represents the lion. This turned out to be a pretty difficult task because we almost headed into PG-13 here just a little bit. Because the Nemean lion's hide was this kind of golden material that was impenetrable by arrows, and Heracles fired a number of arrows at the lion, absolutely no effect. So the only way that he was ever actually able to defeat this thing was the lion lived in a cave, right? He sealed off one entrance to the cave, covered the other one with some kind of a barrier so it would be dark in there, so he could kind of sneak up on this lion, and he strangled it to death. So that was the first Herculean labor was, and you can kind of see this painting. This is by Paul Rubens, sometime in the 1600s, and this shows him killing this. And once he performed this feat, he actually was able to skin the Nemean lion, and he often wore its hide and its head as partially a battle trophy, but also armor, basically, because it was this impenetrable hide. So if you see representations of Hercules, I don't know, did anybody see the movie that came out? I don't know, maybe 10 years or so. I'm not a big fan of movies like that, so I did not see it, but some of the scenes of Hercules in that, he's wearing a lion head, and that's the other representations of Leo the lion. This one's probably not so obscure, but the Metro-Goldwyn-Mayer film studios have used the lion as their kind of trademark for quite a while. I actually linked to a YouTube video here. That didn't work. No surprise, I guess. But anyway, so when you hear that roar, right, that's this old thing. And the original Leo the lion was actually the one that roars in the really old movies, the ones that are probably from the 20s and 30s. And that lion was actually in several of their movies, too. It became kind of famous, actually. Anyway, sorry. So anyway, so what is there to see in Leo? Well, brightest star is Regulus, Alpha Leonis. It's actually a binary. There's a binary component and then another one, so it's kind of a complicated system. But the primary for Alpha Leonis is a bright star. It's 20th brightest star in the sky. It's a subgiant type of star, and one of the things that's kind of noteworthy about it's a B type. We talked a little bit about star types last week, so this would be, on that scale of the "Oh, be a fine girl, kiss me." This is one of the brighter and one of the larger ones. It's also probably just about done fusing its hydrogen. So remember last time we talked a little bit about how stars work, right? And they work by fusing hydrogen into helium and then helium into heavier elements and so on. So this one's probably just about done fusing its hydrogen, which means it's going to fairly soon, on an astronomical time scale, pass into the period of time where it will begin to to burn helium, right? It'll get bigger and redder and cooler in response to that. This is also one of the ones that, it's another very fast rotator. That's one of the things that B-type stars tend to be. Sun, it rotates much faster than the sun. And because of that fast rotation and a few other things, it's also one that experiences a lot of what's called gravity darkening, right? So as the star rotates very quickly, it tends to kind of concentrate the mass along the equator. So it tends to be much brighter. So if you can kind of see a photometric representation of this, the central band, the kind of area around the equator, is like 6 times brighter than what's around the poles of it. Basically, it has this very strong gradient of brightness across it. Even almost all stars do, but it's really much more pronounced in Regulus and stars like it. The other thing that makes it kind of interesting, anybody here ever do celestial navigation? You ever learn how to use a sextant and all that stuff? We actually had the very first astronomy class I ever took in college, we had to learn to do this, which was kind of, I don't know, I mean, if I'm ever lost at sea and have a sextant with me, I guess I'm okay, right? But it's one of, Regulus is one of the 2, I think there's 50 navigational stars, if memory corrects, 59 is it? And Regulus is one of the 2 in Leo. The other is Deneb, which is also a pretty bright and prominent star. So this is one, if you go out, you see those old pictures of, I saw a photograph from probably the early 60s of an airplane, right, flying a big jet, and there was a guy standing up in the cockpit with a sextant, and I guess it's either this was staged or boy, are they lucky they found where they were going. Because, I don't know, based on, maybe the guys they hired were much, much better, but I remember not doing a particularly good job of finding myself with the sextant. But anyway, so this is one of the 2 one of those 50-odd navigational stars that I assume, even in the era of GPS, there are probably people that still know how to do this, just in case the GPS satellites all fail and, got to figure out where we're going. Anyway, so that's one of the some of the characteristics of Regulus. This is the Leo.
So if you go back, that little fuzz patch above Regulus is not from Regulus. That's a dwarf galaxy that sits above.
Oh yeah.
I was wondering about that.
Yeah.
Further out, much further.
It's much further out. But it's very close to, and it's so hard to see, but you can actually pick it up with CCD.
Yeah. It's not too close to Regulus to get. I mean, that must not be. It shows up pretty nice here.
Yeah, like I say, it wipes it out mostly, but you can, through processing, you can bring it out.
Okay, cool.
It is a little dwarf galaxy.
Yeah, little dwarf galaxy.
Yeah, well, relatively speaking.
Yeah. Here's some of the deep sky objects. This is the Leo triplet. It's like kind of right here by the Leo's hind leg, I guess. M65, M66, and NGC 362. I know this one is called the Hamburger Galaxy because I guess it looks like a hamburger. Russ, have you ever done any of these? Or interested in these? Yeah. I don't know. I just thought that was.
It's actually, isn't that part of the sickle? Oh, no, I'm thinking of something else.
Yeah, I think there are a few things.
There's another trio that sits near the part of the sickle anyway.
Yeah.
But not this one.
Anyway, I just threw that one in there because, Hamburger Galaxy.
Yeah.
It's like we're running out of names or something,
I'm guessing the NGC one is not a Messier object because he didn't see it.
Yeah.
So I wonder which one.
It's, that one is a little bit fainter and it's more spread out, so it's, the other 2 are very obvious, but when you get to that one, it's a lot fainter.
Do you know which?
Messier made out of those.
Do you know which one in that picture?
Yeah.
Is it the bottom one?
No, Messier's?
No, the NGC.
The
Oh, it's the longest hamburger.
It's the Hamburger.
Okay.
And finally, I always am interested in meteors and meteor showers. So there is a prominent meteor shower, the Leonids. The thing is, they don't really show up this time of year. I think the best time to see them is typically sometime in November.
November 17th.
Yeah. And they kind of come from the radiant is coming from the sickle area here. This kind of, this little diagram here kind of shows where they're overhead in November. So this is November 18th of, this would be this upcoming November. And they'll be overhead if you're, I guess that would be what? Russia?
Ukraine.
Balkans.
Anyway, so that's where they'll be overhead, but they should still be pretty good. These are ones that I can remember watching as a kid. You know, we had house had a really good view off it in the direction where these were shown, so these were always ones that we would go take a look at in November. Okay, so questions or comments? Okay, so tonight's presentation, craters. Kind of picked this one for a couple of reasons. First of all, because it's kind of a important birthday in the history of craters, I guess. But also because, like a lot of things and a lot of personal interests of mine and a lot of my kind of astronomical interests, I got interested in craters quite a long time ago during a family vacation. So when I was about 11 years old, my parents loaded us in the old Datsun and took us to Mexico, right? My very first trip outside of the US. And we went down through Arizona, and my dad, who was a curious man, thought we should stop at the meteor crater. And so we did. We stopped at this crater that's in Arizona, which some of you have been to, right? Probably many of you have been to. And I was, absolutely dumbfounded by this thing, right? It was absolutely amazing to me. And so I've always kind of had a little bit of an interest in impact craters. And as I've kind of come to learn more about earth science in general, I've been kind of struck by the importance of them. So this goes back to my youth. This is me visiting the meteor crater much later. Obviously, this is a much more recent picture, but I've gone back there several times. I've never been able to go to the bottom of it. I've always been told you can't. Have you?
You can't now.
You can't now. Could you at one time?
You could have one time. Actually, I had an opportunity to go to the bottom of it, but I didn't, because we were running late.
Yeah, I would really like to go sometime, but yeah, it's.
You can't get down there anymore. They've got the fenced off.
Yeah, that's kind of what I said. I guess you can walk around the rim
Yeah.
of it. And it's kind of in a geologically interesting area. There's these fault lines that run through it. If you ever look at it from above, it almost looks square. And part of the reason for that is it's this kind of local faulting system that it sort of interacted with during the impact. But anyway, the meteor crater, or Barringer crater as it's more properly known, was the very first confirmed impact crater that was ever seen. So we'll talk about that a little bit more, but I just kind of show this because it's just a place that's always been kind of special to me. I think if I go back again, I will not wear that hat, but and maybe not a black t-shirt, but anyway, I hope to make it back there again because it's just a fascinating place. Anyway, so when we think about cratering, I think first thing I always think about is the moon, right? Because it's so obviously cratered. And if you kind of look at a contrast here between an object like the moon with this incredible degree of cratering on it, and you compare it to the Earth, it's kind of tempting to arrive at either the conclusion that the Earth has no craters, or the question of why does the Earth appear to have no craters, or both. And it's not just the moon, obviously. Almost any solid solar system object, any object that has a solid surface in it, is heavily cratered. That was actually one of the big surprises from some of the early probes that were sent to Mars, for example, during the 60s, is it came back, I don't know what the expectation was, but it returned images that were heavily cratered. The cratering looked rather different than it did on the moon, but it was still fairly heavily cratered. Mercury, heavily cratered. This is actually one of the minor planets. This is Ida, but it's also pretty heavily cratered. Even Venus, which we can't see the surface of, but we can look at it with radar and things like that, turns out to be a fairly heavily cratered one itself. So it kind of raises this question of, why is it that the Earth is apparently an exception to all this? And of course, the answer to that obviously is that it isn't. The Earth is actually cratered as well. but not quite in the same way that some of these other ones. Of course, we actually kind of implicitly sort of overlook this sometimes, I think. I think it's kind of interesting that there's this place called Craters of the Moon National Monument, but there's really no Craters of the Earth National Monument that I can think of. There's a few places that have been preserved that are craters, but nothing quite like this. So, it turns out, though, that the Earth is, in fact, cratered. And there's about 190 known craters. Of course, again, the next question that I would ask is, why is it that there's, and I think it's up to 193 now. There was a recent discovery of a crater under the ice in Greenland that I think was found through ground penetrating radar. So I think that one was the 193rd crater. But anyway, there are, in fact, a number of known impacted craters on Earth. So that also kind of brings up this question of, why is it that all these other things are so heavily cratered and the Earth is not? So here's some examples of fairly visible craters that you can see, and you can see they come in a real wide range of sizes, right? Here are some relatively small ones. That's a crater in Australia, about half a mile. There's Barringer Meteor Crater right there. This is the biggest one I've ever been to. This is Manicouagan Reservoir in northern Ontario in Canada. That's an impact crater that's about 62 miles in diameter. It was not recognized as an impact crater until a dam was built, right? And that dam backed up this Lake Manicouagan, this kind of ring-shaped lake here. So it's one of the known impact craters.
How old is it?
It's about 56 million years, I think. It's one of the older ones. So here's the largest one that's known. This is Vredefort Crater in South Africa. You can see that it doesn't really show a whole lot of visible sign of it, but you can kind of see this arced structure here to it that kind of gives you a little bit of a visual impression of this. The smallest one, there's really no general agreement on what the smallest impact crater is. This is Dalgaranga Crater in Western Australia. It's about 80 feet across. This is actually this may be it. This may be the smallest known impact crater. This was in Schwanstein, Germany. And that one is, there's probably a 20 centimeter scale right there. So that's a tiny, tiny, tiny little impact crater there, basically. Knowing the Germans, it's probably filled in by now. But it's the point is that there really is no recognized smaller.
There's one in Odessa, Texas, that's probably pretty close to that size.
To this size? Oh, wow. Okay. There is that one that's kind of bigger there. You used to be able to get to it, and I'm not sure that they let you anymore now. But
last time I was there, it was just open.
Yeah.
Not even a fence around.
Really?
Yeah.
Mm-hmm.
You had a hard time finding it.
Yeah. Well, and that's another thing that, we have a hard time finding it as kind of an ongoing theme, right, with impact craters on Earth. And I mean, I think the reason for that, there's no secret to this, right? One of the things that makes the Earth different from every other solid object in the solar system is that we have this very erosively active planet, right? It's water and wind and ice and all these erosive agents, and they operate very, very fast, right? On a geologic time scale, they can operate extremely fast. And so those have a tendency to remove, or at least remove the visual evidence of cratering. So at one time, probably all these craters looked very similar to ones that you'd see on other planets or in other places. But time and erosion have kind of taken their toll on them. The other thing, one of the reasons why we may not see extremely old craters, one of the epochs of cratering at a time when a lot of the lunar craters were formed was several billion years ago. Well, we have this very fast erosive process, right? Wind and weather and that sort of thing. There's this much slower but much more comprehensive process, plate tectonics, right, which is continually sort of recycling the surface material of the Earth. And it operates on a much, much longer time scale. But it's quite likely that some of the evidence of a very, very ancient impact, we'd be talking about, Hadean era impact, would be would have been removed now by tectonic processes. So this is clearly the reason. The other thing is that the Earth is a really biologically active planet as well, and that exerts some kind of erosive forces as well. So as far as how craters form, I mean, it's not exactly a secret. Some object that's heavy enough to pass through the atmosphere and moving fast enough to make a hole in the ground collides with the Earth. Depending on the speed and the angle and the composition of the body, it can make craters with a number of different appearances, but mainly the division is between what are called simple craters, which are basically just a hole, and complex craters, which are kind of a hole, but they have this sort of central peak basically in the center of them. And you see evidence for both of these types of craters, both here on Earth and on the Moon. The process behind these is, as I said, kind of depends on the composition and the velocity of the impactor itself. One of the things that typically doesn't matter, and I was a little surprised to learn this, is the angle at which it hits. Unless an object hits at an extremely oblique angle, it will still make a circular crater, and it will still have the appearance very similar to one that may have hit flush, hit straight down. So what typically happens is you get this impactor, this object, impacts the ground, releases a shock wave through the ground, and that actually alters the subsurface geology. And that's one of the real important clues that helped identify impact craters which may not have much visual evidence left for them. And then also injects all this material up into the atmosphere, and in some cases with very large impacts, it can inject enough material up into the atmosphere to actually cause temporary climate disruptions. That's thought to be what happened in the collision. It's thought to have resulted in the extinction of the dinosaurs. Right, this object was struck the ground, pulverized a lot of material, injected up into the atmosphere, probably up into the stratosphere, where it would remain in residence for a very long period of time and disrupt the climate. In the case of complex craters, the impact is big enough that you get this little rebound in the center. And you can kind of see this. If you've ever taken I don't know, milk or something, and a dropper and dropped a droplet of milk, you notice how it kind of makes that little rebound, right? That's kind of similar to what happens in a situation like this, except instead of it then spreading back out again, it kind of stops in that. So you get this this kind of rebound, and you end up with that central peak. And then, of course, almost immediately you're going to get a lot of erosive processes and geological processes happening along the rim of the crater, and that's one of the things that also is used as sort of a detection criteria for them. So here's a couple of examples of these are simple and complex craters. This is actually lunar craters, but they kind of illustrate the idea. So there's a simple crater. You can see it's just this kind of bowl. Actually, this is a Martian crater. You can kind of see the bowl-shaped thing here. You can see the kind of ejecta blanket around here. This is also an example of a type of crater which is fairly typical on Mars and not unknown on Earth, where the impact is into wetter surface, basically. So instead of it hitting a real solid object, it's almost like it hit a mud puddle or something, and that can alter the effect of it a little bit. This is a lunar crater, and you can see the very, very prominent central peak there. Some of the lunar craters that you can see easily through telescopes, like Tycho, for example, have that structure to them as well. So here's a few examples of craters. This is Lonar crater. This is in India. Has a lake in it, which is not that unusual. There's quite a few impact craters that are also lakes. At one time, meteor crater during the Pleistocene, during the second most recent geological period, when it was during the last glacial period, there was a lot more rainfall in the southwest, so the Great Salt Lake was much bigger then, and meteor crater was actually a lake at that time. So if you go down and kind of dig around in the bottom of it, there's lake sediments down there. But this is Lonar crater. This actually has some religious significance to it as well. It's considered a sacred place in India, so you can see this little temple here. This is one in Australia, Wolf Creek crater. You can kind of see the remnants of it there. This is actually kind of a compound crater. There's this internal bit here, which is probably the remnant of that rebound peak. And then you can see a crater rim around here as well. This one's in a fairly arid area, and a lot of the best preserved craters are for, again, probably fairly obvious reasons, right? Low erosive environment. So Gross Bluff, also in Australia, kind of a complex rim structure to this one as well. This is two relatively recent, probably within the last 15,000 years, impacts. This is Aurelia Lakes in Greece. These are both relatively small and relatively simple craters, both formed in the same impact event, right? This would have been like a double header, two objects that struck relatively close to each other. And again, that's something that's not all that uncommon. There are clusters and chains of craters that are from the same impact event. Kali crater, also a relatively small one. Oh, what was noteworthy about this one is it was impact into igneous rock, right? The ones that tend to be the best preservation environments are sedimentary rocks, right? Water deposited rocks. Igneous rocks are rocks that are created from cooling of magma and things like that. So they tend to be much, much harder. So this is an impact into a harder substrate. This is one that is actually in Sahara somewhere. And what was interesting about this one is, at least to me, was it was discovered by people on Google Earth. Right? People were just looking around on Google Earth and found this thing, and it was previously unknown. So, and it's been now explored and all. It's relatively small, relatively simple crater. So, if you need a hobby and you're really patient and you have Google Earth, this may be the hobby for you. There's Manicouagan again. Again, the very, very large crater. For a while, people thought this may have been the impact that resulted in the Cretaceous Tertiary extinction event, right? The dinosaur extinction event. Now it's been fairly clearly demonstrated that it's a Chicxulub. It's a crater just off the coast of Mexico. But for a while, it was thought that this was at least a candidate for that. And it's, like I said, it's quite large. It's like somewhere in the order of about 100 kilometers across. And Manicouagan is actually kind of interesting because it's also thought to be part of a crater impact chain. But it also kind of relates to the question that was asked earlier about when did this happen, right? At the time the Manicouagan impact happened, and I'm sorry, I gave the date completely wrong. I said 65, it's 214, so I'm off by almost a factor of 4. I'm sorry about that. If you consider where the continents were during that time, there are several known craters. There's the Manicouagan crater right there. This is Rochard in France. This is one in Canada. And this Red Wing crater is in North Dakota, I believe. And they all kind of line up with each other. And they all are similar ages, and the material that's been recovered around them is all relatively similar. So the supposition is that this was a part of a multiple chain impact event, right? Several large to very large objects impacted, which would have been a really bad day for that particular day. But at any rate, so it's thought that Manicouagan is part of this crater impact chain. You can't always see this thing, by the way. I learned about this one actually by accident. I was visiting Iowa. I was actually going to a conference, I think, or something in Iowa City. And they were having kind of a nature day, basically, so I went out to this, and they were talking about the Manson structure. Turns out the Manson structure is an impact crater that is so old and so eroded that there is no visible sign of it on the surface whatsoever. So it's located kind of here, sort of central Iowa. This is what it looks like on Google Earth. You're not going to find anything here. This looks like farmland. The only way that you can look at the size of that thing, now that line right there is 5 miles, right? 5.35 miles. So that sucker is pretty good sized. The only way that we know it's there is by looking at the subsurface geology, right? And looking, and I believe this was discovered by drilling water wells, right? One of the things that happens when you drill a water well typically is some geologist will probably keep the core because there's geological information there. When I was in grad school, I actually worked for a summer for the group that in Nebraska that did this. They kept well logs, and they kept all of these cores, and so you could go look at these things. So this is how this was actually discovered. And what they found was that there were all this geological evidence of this very large crater. There's breccias, which are broken up rocks, right? There were shock transformed rocks that showed evidence of an impact. And all these kind of added up to the idea that this was this very large impact event. And so this has been mapped out pretty thoroughly. But it's an example, in a sense, of an impact structure that is old enough and eroded enough that it no longer shows any surface impact evidence at all. So one of the other things about the Manson structure and things like it, and really all of these, is they point back to how we know where impact craters are and what the evidence for them is. And for a very long time, there was particularly in the 19th and very early 20th centuries, there was a pretty lively debate about whether the Earth really had impact craters. And part of the reason for that is a lot of geologists thought that cratering on the Earth was almost exclusively due to volcanic processes, and that all these craters that they were seeing, and even in places like what used to be called Coon Bluff, which is now the meteor crater, which is now the Barringer crater, were due to volcanic activity. And it was a really, in some cases, very acrimonious debate. And you can kind of see why, right? If you look at all these structures right here, I mean, I would have a very hard time looking at something like this and then looking at something like Barringer crater, like meteor crater, and not coming to the conclusion that they were caused by the same process, right? But all of these three things right here, this is a crater in Death Valley that I looked up the name of, and now I can't remember, sorry. This is one that's actually in Oregon. It has probably the most prosaic name of all. It's called Hole in the Ground, which is what it is. But I would have a really tough time kind of saying, okay, that's not a volcanic event, if you also knew that there were all these craters, this is Diamond Head in Hawaii, that are absolutely known to be volcanic features. But these are volcanic features. What they mostly are steam eruptions, where underground water gets heated up by the volcanic activity and explodes basically. So these tended to not be eruptions associated with ejecta or magma or anything like that. But they form these craters that really are visually almost identical to impact craters. So this left a pretty lively debate about this. There's other things as well. Here's one that's pretty close to home. This is called Winkler Crater, and this is actually just a little bit north of Manhattan. This is North Riley County. And Winkler Crater and several others up there are what are called kimberlites or kimberlite pipes, right? So a kimberlite was basically just a sort of a mini volcano, right? This is sort of a cross section of these that brought this material up to the surface. Kimberlites are very interesting to economic geologists because they're often associated with diamond deposits, right? The name kimberlite comes from Kimberley in South Africa, which is the world's largest diamond mine, right? Mm-hmm. And it's basically just a big kimberlite pipe, right? There's this myth that diamonds are rare. They really aren't. They're absolutely common. And they're probably formed right down at the boundary between the mantle and the core, and they're brought to the surface by these things. So anyway, so this is a kimberlite. And again, if you just look at this, you think, oh yeah, that's definitely a crater. For a while, people thought it was an impact crater, but it's been shown pretty clearly to be a kimberlite. But it's another example of something that is kind of not easy to tell by looking. So how do you know there's impact craters? Well, that's where we kind of circle back to Barringer crater or meteor crater, which was the very first confirmed impact crater. And this is one of the other reasons why I wanted to talk about this particular thing today. So this is, again, a picture of Barringer crater or meteor crater in Arizona. This is the very first confirmed impact crater. The it was generally accepted by the 1920s that this was due to impact. Here's a couple views. There's kind of an oblique aerial view right there. There's a view from orbit. Basically, I think this is a photograph from the space station or the space shuttle. See how it kind of looks a little squared off, right? That sort of reflects the sort of underlying geologic structure. But one of the reasons why I selected it was the man who kind of championed the fact that it was an impact crater was this guy, Daniel Barringer, and today's his birthday. So, happy birthday, maybe his 63rd, I guess. So happy birthday, Daniel Barringer. Daniel Barringer was an engineer and a mining engineer, and he believed quite fervently that it was an impact crater. He was so convinced of it that he bought it, and he didn't just buy it for the fun of it. He bought it because he thought there would be iron deposits associated with it. Turns out there's not, but anybody who's ever visited there, you can see the remnants of the mining down at the bottom. You remember seeing all those structures down there? That was when they were trying to drill down in there, trying to find what they thought would be this big iron body down there. Didn't work for a couple of reasons. It probably was an iron meteorite that collided, but it probably had broken up so much by that time that there was no main body left. So if you ever get a chance to go to the visitor center, you see that one big piece that's sitting in there. That's about as big as a piece of that thing as it's ever been found. I think the largest piece they ever found was, about the size of that would fit in the back of a pickup truck, except it would crush your pickup truck because it would be so heavy. But anyway, Barringer was interested in this. He formed the Barringer Crater Company, which still actually owns this thing, and it's properly referred to as the Barringer Crater. Everyone calls it Meteor Crater, including me, but that's the proper name for it. But there was quite a debate about this. This is a slide I borrowed from somebody, so it has a little animation. This is a far better slide than I can make. All right. So the sides on this were this guy, Grove Gilbert. Grove Gilbert was a president of both the Geological Society of America and the American Association of Geographers, one of the most eminent of all 19th century American scientists, one of the very first internationally famous scientists. And he thought that Coon Mountain, which is what this was originally called, was due to volcanism. He was absolutely convinced of this. Made several trips to this site, always coming back to his hypothesis that it was volcanism. It's quite likely that he was so, biased in his opinion that couldn't change his mind. It's kind of an interesting case study here of science as well, right? This was an eminent scientist that was dead wrong about something in his field. Barringer, on the other hand, thought it was an impact crater, was very convinced of it. In 1902, he actually got mining patents and essentially bought the land around it. He was so serious about that. And this debate went back and forth, and Barringer drilled and explored and essentially lost his shirt, was bankrupted by this process. However, he kind of showed pretty clearly that it was an impact crater. And Grove Gilbert, to his discredit, basically the National Geographic attributed the impact to him. They basically said Gilbert came up with the idea, and Gilbert never corrected them, which shame on him. This guy was obviously a tremendous contributor to science in many, many ways, but this was not his finest hour. So, we should give a little nod to Daniel Barringer. Right? So anyway, by the 20s, it was pretty clear that there was never going to be anything economically valuable here. But it was also at least pretty clear that this was an impactor, that there was an object involved in all this. Unfortunately, Daniel Barringer died in 1929, having never realized any real economic benefit from purchasing this. Well, that was kind of a long debate, but the person that's probably most important in the study of impacts is this guy, Eugene Shoemaker. Familiar to many of us, our club has gotten, 2 Shoemaker grants? So the Planetary Society offers these Shoemaker grants, which I believe were named after and possibly even endowed by Gene Shoemaker and Carolyn Shoemaker, his wife, who was a prolific astronomer and discoverer of comets. But Gene Shoemaker is generally considered to be the father of astrogeology, and his interest was from the very beginning, was in cratering. I actually saw him give a talk once at an AGU meeting, and boy, he was an excellent and fascinating speaker. Anyway, he explored, as part of his doctoral dissertation, I believe, explored meteor crater, Barringer Crater. And in the process of exploring it and making a geologic map of it, he came up with a set of criteria for what could be used to identify them. And he said there's physical evidence, which is the shape and also inversion of the stratigraphy, material being not just displaced, but being displaced in a very specific way, being flipped over by the force of the impact. There was the shock evidence, which is what was most prominent in the Manson structure, right? This is simply what happens to rocks when something really hard, moving really fast, hits them. They get distorted, melted, and that evidence remains embedded in the geology. And then finally, there's geophysical data. There's gravity and magnetic anomalies, right? Gravity is, you may or may not know, is not uniform everywhere, right? There's areas where it's a little higher, a little lower, and you can use those fluctuations to kind of measure subsurface geology. So these were the methods that Gene Shoemaker came up with to. Unfortunately, he was actually killed in a car accident in Australia while he was there on an expedition to map and explore some of those Australian craters. He died in a road accident, from what I understand. Anyway, so he did his early work at that Barringer crater. So there's another picture of it. I always think it's the coolest thing in the world, so I just keep showing pictures of it. You know, you always have to be dumbfounded by the fact that the thing just missed the visitor center, right? But anyway, it's kind of an old joke, right? But you got to tell it. So anyway, so here's the things that Shoemaker found. At Barringer Crater, he found that inverted stratigraphy. So here's not to turn this into a treatise on subsurface geology in northern Arizona, but this is the sequence of rocks. The Coco Nino and the Toro Weep are sedimentary rock formations, and then the Kaibab. And what you see around the edge of, this is Shoemaker's map right here, what you see around this is that this has been flipped over, right? So you've got some of the Kaibab formation, and then this Moenkopi formation here, and then the Kaibab again, right? And it just shows that this whole thing has just been turned over. And this occurs around the rim, where exactly where you would expect it, right? Where something has been, an impact has flipped all that stuff over. There's also really large pieces of displaced stuff. These are kind of big blocks of this Coco Nino sandstone here. And they're sitting up on the crater rim. There's a picture of one right there. And that probably the thing that you saw through the telescope, they've got that fixed telescope pointing at a rock. That's a big piece of this Coco Nino formation here, which got ejected by all this. So this overturning here was very similar to some things that Shoemaker saw associated with things like subterranean nuclear tests, right? When they still tested nuclear weapons by digging a big hole in the ground and setting them off, right? And they'd make these surface craters, and those craters had overturned edges. And that's a process that's pretty analogous to an impact. So this was, by analogy, he argued that this was evidence of the impact nature of this. So that's the inverted stratigraphy. The shocked rock bit actually came from another impact formation. And somebody mentioned this at the meeting last week, actually. This is the Nordlinger Basin in Germany, Nordlinger Ries. And it's a very large impact structure. Here's what it looks like if you're actually there. You see that kind of raised area there? That's the deeply eroded rim of this very, very old crater. And this quarry right here, this Pulsingen quarry, which was disused, and even when Shoemaker and his colleagues were there, provided a lot of the evidence, because they're quarrying out rock from this to build structures in the little town that sits in the center of this. And there's the town right there, and that church that's in the center right there. This is not circular like this because it's in the crater. It's circular like this because this was a medieval walled city, right? The crater is actually much, much, much larger. It goes way out here. But that church right there was one of the things that was built out of rock that was quarried from those. And if you look real closely at this and the rocks, you see these alterations, right? The rock on the left here has been altered by melting. The impact melted the rock and then it re-solidified, right? And it kind of jumbles up all the components. So all these little blebs, all these little inclusions in here were things that were when the rock re-solidified, right? So that's one big evidence of the impact. These are called shock pyramids, I guess. These are shock things, and you see how it just kind of looks like this rock has been shattered, right, by being hit, and that's exactly what happened. And if you go look at the walls, it's not, I have to preface this by saying I've never been to this town, so I can't give you a first-hand result on this, but people who have tell me that, you know, if you take your geologist loop, you know, that little magnifying glass that they carry everywhere, and you look real closely at this church, which is the St. George's Church, you can really see the evidence of this in these blocks of stone that have been quarried to make it. It shows up very plainly, right? Somebody, one of my more religiously literate friends said it's like the church of the God of Jeremiah, right? The God of the avenging. But anyway, and this is the other things that we're often seeing. This is coesite. These are called shock diamonds or coesites, and this is a type of rock that's formed by these impacts, and these are fairly common around there as well. So all these are evidence that, you know, geological evidence of the ones. I couldn't really find anything good on the geomagnetic influence. I've seen some geomagnetic data for a few craters that were purported to be impact structures, but probably weren't in probably aren't in western Kansas. But basically what the geomagnetic data is just little slight fluctuations really in the density of the surface that causes slightly different gravitation.
Isn't there some in Nebraska too, about
Yeah.
central Nebraska?
Yeah, probably the same event
area.
or the same period of time. The Brenham Palisite, which you have some pieces of, right?
Yes.
This is a meteorite that fell somewhere out in western Kansas I don't know, many
Yeah,
years
I
ago.
wasn't there to watch the fall, but
Yeah.
I do have some pieces.
Yeah, there was a guy, was a geologist, I heard him give a talk once, I believe he was from KU, Wakefield Dort was his name, who had mapped a structure in Nebraska that he was pretty convinced was an impact crater.
Kind of using a magnetometer, weren't they?
Yeah, and grab samples and things like that. He actually claimed it might have happened within human history, that there may have been like Plains Indians verbal evidence of it. Most of the geologists I talked to about it were skeptical, but anyway. But yeah, it's yes, that's exactly right. So, what about craters? I mean, they're kind of interesting just from a purely science point of view, but they also have some fairly significant, some economic significance. So this is kind of an obscure looking little graph here, right? But the thing I wanted to point out here is that basically says that somewhere, what this is telling us is that there's probably somewhere around a third of all known impacts have some economic significance associated with them. And that's because they're associated with mineral deposits and with petroleum deposits as well. So some of these other ones here kind of show how that works, and you can see oil and gas is pretty frequently associated with them, and also precious metals as well. So a few examples of that, or why this happens, right? You get some massive ore deposit below the surface. Very large impactor comes along, smashes into the ground, melts all that stuff, right? Kind of melts the ore body, and also kind of brings it into a little bit more accessible location. So in a sense, it does the same, if you've ever seen one of these big open pit mines where they take big bulldozers and dig huge holes in the ground. This takes care of that problem for you, right? It kind of crushes everything and creates the much more easily mineable. It also kind of helps with hydrocarbon deposits. It fractures the ground, right? Fracking now is a technique that's used in hydrocarbon production, right? They basically inject steam into the ground, it breaks up the rock, and hydrocarbons can then be transported. Again, this kind of takes upward. This is kind of a neat job of breaking up the rock, all by impact. So the point is that it kind of makes for some, there's often an association between economically valuable deposits and impact sites. So this is that Red Wing crater in North Dakota. I mentioned it a little bit earlier. It's probably part of that cluster that was associated with Manicouagan. And it's also really closely associated with some oil or petroleum production sites. So these are production fields, right? This is the Red Wing Creek field. That's the Bowlin field and the Little Tank field. And those are all thought to be associated with this, this very ancient impact, 250 million year old impact or so. Here's one that I have actually briefly seen. This is Sudbury Basin in Ontario, also a relatively large impactor, associated with precious metals, particularly copper mining. So it's thought that probably some copper and some other precious metals in the Sudbury Basin are associated with impact. I don't know why that's there. So finally, just to kind of wrap this up a little bit, I think I must have forgotten to delete something there. So we've kind of talked a little bit about, how what craters are, processes that form them, how we know that they're impact craters and not something else. But what's the practical importance of all this? And this is again something I think that some of the things that are done in the club here are informed directly by some of this. One of the reasons why I think we are involved in some of the NEO work is that it's planetary defense, right? So this is a kind of a representation of what you can expect from objects of various sizes, right? And these really huge ones here that could cause global devastations, there hasn't been that many of them in history, and what that research is probably telling us is there probably won't be any for a while, which is good. That's a very good thing. But there's liable to be quite a few down in this range right in here, where an impactor between, say, about 50 meters and maybe 150 meters, which is not that big, really, right? Could cause locally some very serious effects. So this is why this, the work that Gary and Dave do, kind of helping to fix the orbits of these things, is so important, right? Because it's very important to kind of have advanced warning on this. But one of the things that these craters can do is they can kind of give us some idea of what the potential for these impacts were. Of course, the kind of index case for all this is the Chicxulub crater, which just lies just off the coast of Yucatan. There's essentially its size right there. There's very little in the way of surface evidence for this. There's a little bit of geological evidence in southern Yucatan, but for the most part, the evidence is below the ocean. But it looks like there's a pretty sizable crater down there that's associated with this impact. And this is the one that's thought to have essentially caused a large-scale extinction, including the dinosaurs. It's not really 100% sure if this is the only thing that caused that. It was probably more to it, a little bit more to the story. But it's certain that this impact is associated with a very, very extensive extinction event. So this would be kind of the edge case, right? If something like this hit us, and honestly, it probably wouldn't matter if we knew about it or not, right? But for smaller things, it really could, right? We've had this recent demonstration that it is possible to actually divert the course of these. That was what that DART mission was all about. And this is why this could be important. We probably all learned back in nursery school, right, that the faster something goes, the more energy is released when it strikes something. That's a fairly intuitive thing. This is the exact relationship, right? So this velocity squared term right here is the kicker, because you think about the velocities that most of these objects would be arriving at, it's in the tens of thousands of meters per second. They're extremely fast moving. And you square a number that big and you get a number way bigger. So an object about that big, this is my attempt to use Photoshop, which I'm not really a graphic artist. An object about that big, if you set it on a football field, would probably have made the hole that you see at Behringer Crater. That hole is about 0.8 of a mile across. If you want to translate that, I use Manhattan as an example there. So there's as if it landed in that stadium, if it landed right there, right? There's the crater that you would get, but you would get probably thermal and kinetic impacts going much, much further. So it would cause essentially a fairly large loss of life. It would be a pretty devastating event. And looking at existing craters, though, kind of helps us understand that. It kind of helps us gauge how big these things might actually be. And this, by the way, came from that website where you can actually, simulate your own asteroid strikes, which, I don't know, it's kind of fun. All right, so that's it. If you really want to delve into this more deeply, there's this thing called the Earth Impact Database. I built a link to this, which apparently is not working, but it's a database of all the known impacts with all their known characteristics. So if you're curious about this and you want to follow up, this would be a good place to go. All right, questions? Anything? Comments? Yes?
We went to Decorah, Iowa,
Uh-huh.
and I don't know, 10, 15 years ago, they determined that there was an impact crater there.
Yeah. Is that the one that there's been a lot of meteorite finds associated with? There's some place in Iowa that's been it's near one of the Amana colonies, I believe, where there's been quite a few meteorite finds. I don't know. There used to be this show on TV called Meteorite Man. Did any of you ever watch this? I loved that show. I'm really sorry it's no longer on. But one of the places they went was Iowa, and they were finding. It was I want to say it was near one of the Amana colonies. Is that near Decorah?
I'm not sure. Like brought some pictures.
Well, we should see them. But, yeah. I think there's the Odessa one in Texas. There's one in like Tennessee or something somewhere that is thought to be an impact structure.
Northwest Tennessee?
I think so.
Clarksville?
Something like that, yeah. I don't know, is that a pictures from Decorah?
Yeah, and there's some in Oklahoma too.
Yeah. Anyway, that's all I got.
To do a less mathematical model, when he was talking about the velocity factor, if you take a quarter and you throw it at somebody, they throw it back. This is one thing I've used a lot. And you throw it back, and then you take that same amount of mass, you shape it into a bullet, stick the gun. What's the difference? The difference is I go to jail for a very long time. Well, mostly. But it's just velocity. It's just velocity, same amount of mass.
Yeah. Well, yeah, kinetic energy.
And figured that speed of that bullet coming out of the gun is about 20 times slower than most meters.
Yeah.
When I was out at Meteor Crater, they told us they had a little figure down in the bottom where it was supposed to be an astronaut, and when you're standing up there looking at it, it was like very small.
Yeah.
So it shows you how big that thing was.
Yeah, yeah. I think it's somewhere on the order of about 0.8 of a mile across or something like that. It's more than a kilometer across.
Huge.
Yeah. It's yeah, I think they used it as a training site for the Apollo missions. They used it to train the astronauts.